So let's continue our attempts of drawing how the Steiner circles move around. And we know from these transformations that we observed that it is elliptic, so it will be a rotation of the Steiner circles of the first kind along Apollonius circles. And we considered a circle gamma 1 which goes through the fixed points and has this segment in 6 points as a diameter. There are other, of course, there are other Steiner circles of the first kind, and we can draw some of them. Must be circles, right? There we go. Like this. And maybe some other circle. This. We don't want to make this picture very messy, so we won't draw them for now. We just concentrate on this circle gamma 1. And the gamma 1, as a result of this transformation, moves into the imaginary axis. That's what we discovered. And how does it move around? I guess we can so I will draw this circle, make it more evident. I will make it blue. And then it moves into the imaginary axis. How does it move? I guess there must be some, I will erase this for now because it will hinder the clarity of what we would like to see. And I will draw in dotted lines the Apollonius circles, the circles of the second kind. So I guess there must be circles in which points I and the origin are symmetric. So this circle must be orthogonal to our circle gamma 1 and to other, of course, circles of the first kind. So it must look somewhat like this. And maybe there will be another circle like this, and maybe another circle like this. And our circle gamma 1, this blue circle, will move into the imaginary axis. How will it do? It's being rotated through negative 90 degrees, so I guess it will go like this. Rotation in the negative direction, something like this. Something like this. Something like this along another circle. And what about here? I think it will go something like this from oh no, the other way around. Actually, yeah, our circle goes into differently. Our circle gamma moves into the imaginary axis, so it must go like this, right? And this is right as well, and this will be right. It should go through in the negative direction of rotation, so 90 degrees in the negative direction, something like this, and something like this, and something like this. You will say, oh, this is in positive direction. This is in the positive direction about the fixed point that becomes infinity. Remember infinity is sitting in the north pole and 0 is sitting in the south pole. So the rotation that is seen from the south pole counterclockwise, the negative direction, from the north pole, from the infinitely removed point, will look clockwise. So it must be something like this. It must be something like this, maybe also this. But what I would like to do, I would like to draw at least one circle of the second kind to obtain its equation, to make a precise picture and to show how the rotation is occurring along an arc of this circle. So I will remove so far these approximate pictures, and I will try to get some precise pictures. So we don't know, this circle is approximate. Is it orthogonal? Is it? Are these points, fixed points, symmetric in it? I don't know. Let's make a precise picture. So I will erase this, all this stuff, and I will just leave our circle gamma 1. Now there is a good question. What about this circle? This circle of the second kind. It is clearly one of the clines orthogonal to gamma 1, right? It's a straight line, but that's what happens. Yes, there is one of them a straight line, others are circles. So it's also a cline. It's also a cline, yes? I will denote this cline somehow. Why don't I call it cline number 1? I will call it cline number 1. I think I will take the right stuff. And this cline number 1 seems like we can suggest that it just moved into itself. Really, this transformation is elliptic. So what happens in the ZW plane, ZW capital plane, with Apollonius circles, these circles, Steiner circles of the second kind, they are being rotated, right? And when you rotate this circle around itself through negative 90 degrees. So that's what you get, like this. Of course, the circle comes into itself, right? What happens to lines? Lines are being rotated. Yes, imaginary axis is being rotated into the real axis and vice versa, right? Maybe some other lines of the first kind, yes? Some gamma is being rotated through negative 90 degrees, so it becomes this, right? But as for circles, when you rotate a circle, it still stays onto itself. And we can guess that this is the circle right in the middle of our universe, this cline, C1. It's right in the middle, yes? So it will be probably the unit circle. Yes? If you recall the Riemann sphere, what stays right in the middle between the circles which surround infinity and the circles that surround 0? The unit circle, right? The circle when with the Riemann sphere. This is a cross section onto the complex plane, right? This is North Pole, somewhere there on the other side of the globe is the South Pole, right? The rotations around South Pole, which go in the negative direction like this, go around North Pole in the positive direction like this. So, in the positive direction, yes, I show it just constant. So, and this is the unit circle, right? This is one. This is one. This is one on the real axis. This is one on the imaginary axis. This is I. So let's see. Let's try to do it by means of calculation. We trust the symmetry, but once in a lifetime, we will check by calculation. We will ask, is T of C1 again C1? We will perform transformation, yes? So how do we form C? S of C1, first of all. So we have this equation, Z equals Z over Z minus I, right? So, you can find from here, and we already found it, that Z minus I equals to Z, and Z minus 1 equals IZ. So Z is IZ over Z minus 1. We found it already once. Before we found it, I just repeat quickly. And Z conjugate is negative IZ conjugate divided by Z conjugate minus 1. And we substitute these two into the equation. We substitute these two into the equation of C1. C1 is imaginary Z is 1/2. So Z minus Z conjugate 1 over 2I, Z minus Z conjugate is 1/2. So 1 over 2I, and here we will write this expression IZ over Z minus 1, IZ over Z minus 1 minus I Z conjugate minus negative IZ conjugate divided by Z conjugate minus 1 equals 1/2. Let's multiply by 2. Let's reduce by I. You can bring in I inside the brackets and cancel this I. So it will be Z over Z minus 1 minus Z conjugate over Z conjugate minus 1 equals 1. So, not much wrong here. Multiply by Z minus 1, Z conjugate minus 1. It will be Z conjugate minus Z conjugate minus Z conjugate equals Z conjugate, multiply Z minus 1, Z conjugate minus 1 will be here, right? Minus Z minus Z conjugate plus 1. So, is it right? No, it's not right, because it must be plus here, right? It is minus and another minus, and we reduce by I, so it must be plus here. So it will be plus here, and here will be Z is equal to minus. I think it is right now. What happens? This cancels with this. this cancels with this cancels with this. What's left? Z conjugate equals 1. It means modulus z squared equals 1 or z modulus equals to 1. So it is a unit circle. It is a circle of radius 1, ZW plane. This line, C1, moves into the unit circle. This line C1 moves into the unit circle. And when I rotate this circle, through 90 degrees or through any other angle, it goes into itself, right? What happens? The circle stays on its own. So W in W plane, it will be still W modulus equals to 1. So W small over W minus I modulus squared is equal to 1. Right? This is the expression for W. Or W over W minus I, W conjugate over W conjugate plus I equals to 1. Multiply by the terms in the denominator, so we'll have W conjugate equals W conjugate minus IW minus IW conjugate and plus 1. So somewhere mistake. Did I? Yeah. It will be WW conjugate minus IW conjugate and plus IW. Here will be plus. Now it is good. So these two terms cancel each other. What's left here? I W minus W conjugate equals I will take 1 to the left hand side, negative 1. Or what is this? W minus W conjugate equals 2I real imaginary part 2I imaginary part of W. So I multiplied by 2I imaginary part of W is negative 1. I times negative 1 is I times I is negative 1, so negative 2 imaginary part of W is negative 1, or imaginary part of W is 1/2. Oh. So really C1 is mapped exactly into C1. And we return to W plane as a result of T transformation. Right? So it is one of our Apollonius circles. And along these Apollonius circles we have a rotation through negative 90 degrees around the origin. Gamma goes into the imaginary axis. It will go this way. And you can see that from this point it will go as if it goes in the positive direction, right? As if it goes in the positive direction. So we checked that as a result of T transformation, gamma 1 moves into the imaginary axis. And you can check, just perform this calculation, that imaginary axis is also one of the Steiner circles of the first kind, yes, because it connects these two fixed points. Also goes into gamma 1. And we did not calculate this, but you can verify on your own. It's a good exercise. And therefore, this move happened, and the imaginary axis, where does it go? It goes here. Okay. So, I want to have a better picture. This is one of the Apollonius circles, yes? This line C1 is one of Apollonius circles. It's easier to call them Apollonius, it's faster. One of Apollonius. I want to have at least one more Apollonius circle. So what I do? I want to write an equation of an Apollonius circle that surrounds point O, and I want to see how the motion will happen along this circle. So, in order to see this, but I don't know how to write an equation of Apollonius circle of this, of the second type, because I don't know where is the center. Where is the center? I call this C1. It's not a very good name. Let's call it something C5, because I have C1 reserved for another circle. Yes, so this will be C5. There are infinitely many of these circles, so numerate them whatever you want. So this will be C5, this straight line through the 1/2 between 0 and I. Halfway between 0 and I. And I want to consider another line. How do I know? How do I write equation of this circle? Because these circles, they don't have center at this point. And where is their center? Where is the center? Center of Apollonius circles. Centers of Apollonius. How to write their equations? I cannot. But what can I do? And it will be a very popular trick in our calculations. It will be a very popular trick in our calculations. I know equations of Apollonius circles in ZW capital plane. In ZW capital plane, Apollonius circles have equations. What equations do they have? Modulus Z equals to something, okay, some numbers. Yeah? So they're all centered at the origin, so it's pretty easy to write their equations. Let's choose, we want one circle, yes? Let's choose circle C1, now I give it name C1, modulus Z equals 1/2. Why 1/2? Don't ask me. But I advise you to consider another circle with equation, for instance, modulus Z equals 2 or 3. Take number. Don't take number 17 because calculations will be difficult. Take some easy number. If you want, you can take number modulus Z equals to K and perform calculations, but I would prefer to take a specific number. Okay? What is the pre-image? I will say modulus z squared equals to 1/4, and z is z over z minus I, right? So z over z minus I multiplied by z conjugate over z conjugate plus I, this is z times z conjugate, right? Equals 1/4. Equals 1/4. The calculations are not too long, so let's do it. So let's multiply both sides of equations by 4 and by z minus I by z conjugate plus I. So it will be 4z z conjugate equals z z conjugate plus I z minus I z conjugate and plus 1. Bring everything to the left hand side. We will have 3z z conjugate minus I z plus I z conjugate minus 1 equals to 0. Right? And then I will multiply by 1/3 and then complete the square as we always do. So it will be z z conjugate plus 1/3 z conjugate plus I, sorry, plus I over 3z conjugate minus I over 3z minus 1/3 is equal to 0. Factor out z conjugate will be z plus I over 3 minus I over 3 z plus I over 3 minus I over 3 and minus 1/3 is equal to 0. It's our regular trick on completing the square, right? We had here factor out z conjugate, we have here I over 3, negative I over 3z, so we did it like here, z plus I over 3, and we, to be honest, right I over 3. So we have z conjugate z plus I over 3 minus I over 3 z plus I over 3, and here will be negative I over 3 and negative I over 3 minus 1/3 equals 1/3. Okay, so and it will be negative 1/9 equals 1/3. Okay, did we do everything right? No, I didn't do anything right because here it will be plus 1. No, it looks okay. So factor out z plus I over 3, and here will be z conjugate minus I over 3 equals 1/3 plus 1/9. One-third plus 1/9 will be 3/9 plus 1/9 will be 4/9. right? 1/3 plus 1/9 will be 3/9 plus 1/4. It will be 4/9. Or it will be modulus of z plus I over 3 equals 2/3. So a circle of radius 2/3 centered at negative I over 3. Okay, let's draw this circle. Let's draw this circle. So I will, again, remember the idea, yes? We started with a simple circle whose equation we know in the z-plane. It's very easy. Equations of circles and equations of Steiner circles of first kind in the z-plane is also easy. They are straight lines. So here, this is 0, this is I, right? We must center at I over negative I over 3. So approximately, let's split it into 3 equal parts. So it will be approximately like here. This is a point negative I over 3. That's where the center will be of this circle. And the radius is 2/3. So this plus this. So it will be like this. Circle. Here is a circle. Here is a circle, which is the circle which we called C1. And now we are happy because we can now show how gamma 1 becomes the imaginary axis and how imaginary axis moves into gamma 1. How shall we do it? We know along this arc. So we'll draw this circle. Oh, I'm very sorry. Of course I made the wrong picture. My apologies. In my picture I took the center as the 0. No, it's not right. I erase everything. Again, this is 1/3, 1/3. This is distance between 0 and I is 1. So I split it into 3 equal parts. So this will be point negative I over 3, right? And the circle will be centered here and of radius 2/3. So it must go like this. I don't want it to be red. I will make it dotted line circle. This is how it goes. This is how it goes. This is a circle. This is a circle. See. Now, our rotation occurs from gamma 1 to imaginary axis along this circle. That's how it goes. For imaginary axis, we didn't check it, but I asked you to calculate. And this is how it goes. What else? From gamma 1 to imaginary axis. That's how it goes. And that's how it goes from here. What do you think about the upper part? I can bet that there must be a circle symmetric to this one around I. How can it not be here? Can you tell me? No, I cannot tell. But if you want, you can check by calculations. And how do you check by calculations? You can try to take line number 2 such that in the z-plane the equation of line number 2 will be modulus z equals 2. It will be symmetrically located with respect to the unit circle. So I guess, it's my guess, but my guess is pretty good here. And here it will be a circle symmetric to this one. So the center will be 1/3 unit above I here, at the point 4/3 I, and the radius will be 2/3. So it's something like this. So it will go approximately like this. Approximately like this. Right? Try to make it as round as I can. And when you do this in your notebooks, on your paper, please use drawing instrument, use a compass. So here it is. What do you think will happen? How rotation will go? It will go from gamma 1 to the imaginary axis like this. Again, you say it goes in the positive direction. How can it be? You had rotations through negative pi over 2. But yes, it was negative pi over 2 around the origin. Around the infinity, it will be looking in the positive direction. I think that's a good picture that we have. We may add here, what can we add to this picture? We can add other circles of the first kind and other circles of the second kind. And I did these calculations, and I would ask you also to do them. And I did these calculations in a certain way. Again, this is a convenient circle. What is another circle we can take? Should we draw a circle with center here, here, here? We can take any point on this line and write an equation of a circle of radius distance from this point to the origin, or distance from this point to I. Yes? So we can actually take any point, we choose any point here as a center, and draw a circle passing through these 2 points. This will be our, it doesn't look like center is here, it looks like center is here. This will be our Steiner circle of the first kind, and then see how it moves around, and which circle will be its image. And I don't know. Suppose this will be the circle that its image. And then, if one of them is moving to the other by rotations from 90 degrees, probably it will go along some arc like this, it will go along some arc like this, but you can do it something different. You can do it in a convenient way, and the convenient way will start with the Steiner circles of the first kind, start with a line in the W plane. And I did these calculations. And I will pose these calculations on whiteboard, yes? I had a line which I called L3 in W plane. It has equation. Such as this angle tangent alpha is 3/4. Its preimage is, how to get preimage? We rotate this through negative 90 degrees. This will be the one, right? Its preimage is L2. If this angle is beta, so it will be tangent beta is negative 4/3. You know, in order for two angles to make 90 degrees angle, the product of the slopes must be -1, right? And then find Z preimage of L2 and find W image of L3. And you will have two circles and they will move one into another. And these calculations are pretty long, and but they are done in all the details, and I will post this on the blackboard, and so you will have these calculations. Also, there are problems 3A and C in your home assignment, and there is also one more problem which I considered example considered in your textbook, but the picture is not accurate, and I considered it and I made an accurate picture, and it's explained in detail how. Please consider all these questions by Tuesday, and on Tuesday we will discuss it.